So we start today with chapter 8 being corrosive materials. And what we need to kind of start with for this particular chapter is an understanding overall of what a corrosive material is. There's a lot of definition work here on this slide. And the reason for that is because, well, as we've seen in a number of different scenarios this semester, different agencies have different rules and different definitions about what counts as corrosive and what counts as not corrosive. So CPSC says that a corrosive substance is any consumer product that can destroy living tissue such as the skin or the eyes by chemical action. The DOT has a similar definition. Talking about liquids and solids that cause full thickness destruction of human skin at the site of contact. But because we were talking about transport as well, we see that there's an additional piece here dealing with reaction of substances to metals. Since most things are transported in metal containers, a corrosive substance that reacts with those metal containers would be of particular interest. OSHA, again, very similar to the Consumer Product Safety Council. We're talking about a chemical that causes a visible destruction or irreversible alterations in living tissue by chemical action at the site of contact. But we can see that in all three of these definitions, we are talking about some kind of a chemical reaction that is taking place with the substance and usually the skin. But we can also throw in the eyes or certain kinds of materials like metals as well. Again, depending upon what definition we're really interested in, what the purpose really is. So these three definitions do overlap a lot. But it still really doesn't, this doesn't really give us a great idea of what corrosive materials are. It tells us what they do, but it really doesn't tell us what they are. So maybe we need a little bit better of a definition, or at least something a little bit more specific. When it comes to corrosives fall primarily into two categories. Corrosives can either be acids or they can be bases. Now, by definition, acids are substances that will produce hydrogen ions when dissolved in water. And bases are substances that will produce hydroxide ions when dissolved in water. What qualifies something as corrosive or not corrosive has everything to do with the amount of hydrogen ion or the amount of hydroxide ion that they produce. So what's kind of funny is if you look at a simple definition of water and you talk about what water can do to itself, what you'll see is that water can split itself into hydrogen ions and hydroxide ions. Now, this splitting that occurs in water is what gives water its neutral character when we talk about pH, because we end up having an equal amount of hydrogen ion and hydroxide ion, so they more or less cancel each other out. In acids, we'll see considerably higher hydrogen ion concentrations, and in bases, we'll see considerably higher hydroxide concentrations. But in neutral water, we see both in roughly the same concentration, and their acidity and basicity, they kind of cancel each other out. So what else can we say about acids and bases? Well, we can characterize them based on strength. So strong acids. Strong acids are going to give us high concentrations of hydrogen in water. Weak acids are going to give us lower concentrations of hydrogen ion in water. Now, solutions that contain any considerable concentration of ions in water are known as electrolytes. And electrolytes will conduct electricity. That's why they are called electrolytes. One of the ways that we can tell strong acids and strong bases from weak acids, weak bases, is based on their electrical conductivity. Now, there are other ways of going about it as well. We can use pH, we can use chemical reactivity tests. We can do a lot of different kinds of testing. But in the case of strong acids, we see that because they have high concentrations of hydrogen ion, they're going to be strong conductors of electricity. Because weak acids have low concentrations of hydrogen ion, they're going to be weak conductors of electricity. The same is true for bases. Bases that are strong will also be strong conductors of electricity. And weak bases will be weak conductors of electricity. Now, the difference between acids and bases is, again, what those ions are. In the acids, we're talking about hydrogen ion, H+. In bases, we're talking about hydroxide ion, OH-. And so, again, from a chemical formula standpoint, that's one of the ways that we can kind of tell if something's an acid or a base. Acids usually are going to have hydrogens near the front of their chemical formula. Bases are usually going to have OHs near the end of their chemical formula. Now, it's not a hard and fast rule, but it's kind of a good general rule, because there are obvious exceptions in a lot of different directions, especially if we start to look at and consider organic compounds, which really don't follow the same rules as far as how they're put together. As far as acids are concerned, we talked about their electrolytic character already. fact that they will conduct electricity in water. But there are some other key characteristics. Acids tend to have a sour taste to them. There are lots of acid substances in things like citrus fruit, vinegar. A lot of those chemical substances that you know that have a sour kind of flavor to them are in general because they contain considerable amounts of different acids, citric acid, ascorbic acid. Acids are known to turn litmus paper red. So generally litmus paper comes in two different forms. There is blue litmus paper and there is red litmus paper. Acids will turn the red litmus paper red, will stay the same. It'll turn the blue litmus paper to a pink or a red color as well. So often we will see acids kind of color coded with the color red as a result of its chemical action for litmus. The other thing about acids, well known to neutralize bases. When acids and bases come together, they do a neutralization reaction. Now you would recognize a neutralization reaction as just simply a double replacement reaction. The product of that double replacement reaction is almost always water and some other kind of chemical compound. Bases, on the other hand, again, their electrolytic character we've already discussed. But bases are largely responsible for things like bitter flavors. If you have ever, well, this is actually pretty easy. When you think of things like antacids, which are usually basic compounds, not necessarily hydroxides, but basic compounds of carbonates, those tend to have a bitterness to them. Baking soda has a bitterness to it. Bases in general have a slippery feel to them. Not necessarily in their solid form, but certainly when we put them into solution. You run the solution over your fingers kind of slide over each other like you've got soap on. And bases will turn litmus paper blue. Now, obviously, bases will react with acids as well. That's what antacids are all about. And again, they would react in the same kind of form and fashion. Double replacement reaction, giving us water and some other kind of ionic compound. Let's talk about some different types of acids. So acids can be split into some subcategories. The first, probably the most common to us, are the mineral acids. Mineral acids would include things like hydrochloric acid, sulfuric acid, phosphoric acid, nitric acid. Although nitric acid is going to fit into another one of these categories as well. So these are kind of your common laboratory acids. Actually, a number of these acids find their way into your homes in a variety of different products. But generally speaking, there is one element that is missing from mineral acids and from consideration as mineral acids, and that is carbon. If an acid contains carbon, it falls into this second category. a carboxylic or organic acid. These are substances where we have carbon, hydrogen, and oxygen exclusively. The most common of these acetic acid, which you know most commonly as the active ingredient in vinegar. Vinegar is basically a 5% solution, so 5 grams of acetic acid for every 100 grams of solution, 5 grams of acetic acid for every, and 95 grams of water. And so your purest forms of vinegar tend to fall into that line. The difference between all of the different varieties of vinegar largely come from their sourcing. So apple cider vinegar being derived from apple juice. Red wine vinegar being derived from red wine. So on and so forth. Distilled vinegar, white vinegar, that's kind of just, it's kind of its own product. It's made from a distillation process. That's why it's white in color. It doesn't have a natural source usually. But organic acids do make up a good chunk of the acids, but again, far less common. Much more common to see mineral acids in the home. In addition to describing acids based upon their type, again, mineral versus organic, we can also classify acids based upon their concentration. So a concentrated acid is generally high in concentration, and this is usually how you get the acid from a commercial grade dealer. So for example, up in our laboratory, we have hydrochloric acid, we have nitric acid, we have sulfuric acid, we have acetic acid. Those are the 4 acids that we carry in most of our labs. All of those come from a chemical supply company. And when they come to us, they come in these 4-liter containers that are at a very, very high concentration. Some of them keep at that high concentration because we need it. Others of it we will dilute by adding water to bring it down to a concentration that's a little bit easier to use and not quite as reactive or even dangerous. So those concentrated acids usually come with a concentration value. So for example, sulfuric acid comes to us at a concentration of 18 molar. That's 18 moles, 18 units of sulfuric acid for every liter of water. Hydrochloric acid comes to us at a concentration of 12 molar, 12 units for every liter of water. Now, if you contrast that to the majority of the acids that you use, most of the acids you have used have either been 1 molar, 1 mole, 1 unit for every liter, or less, like 0.1 units per every liter. So to go from 18 to 0.1 requires some significant dilution. Why do we do that dilution? Because the necessity of having a concentration that high generally doesn't apply to most kinds of situations. Only when we need a severe amount of corrosive power will we use such a high concentration. So most of our acids end up getting diluted. That's when we add water to that concentrated acid. And as you might expect, diluting that acid is going to help with its corrosive nature. The more we dilute it, the less corrosive it's going to be, the less chemical action it's going to be capable of doing in high quantity. Now, that doesn't mean that diluted acids are not dangerous. They can be. Always comes down to, and we saw this in the last unit, duration of exposure and the nature of the chemical itself. But certainly a diluted acid is going to have far less dangerous effects than a concentrated acid will. Now, the last acid type that is worth mentioning are the oxidizing acids. Oxidizing acids kind of have two things going for them. First, they're corrosive by nature of being acids, but they are also good oxidizing agents. They're oxidizers. And so your most common examples of those, nitric acid is a very good oxidizing agent. And so is perchloric acid, which is a good enough acid in terms of its oxidizing power that we find it being used in firework making, where it can produce enough free oxygen to get the firework materials to ignite when we want them to ignite. So from that perspective, with these two acids in particular, you kind of have a confluence of a couple of nasty things going on. You've got strong acids that are highly corrosive, coupled with the fact that they are oxidizers as well, which means that they are especially reactive. So that's one thing that oxidizing agent acids are going to have over other acids. They can react chemically via two pathways. They can act as oxidizers, and they can act as corrosive agents, whereas non-oxidizing acids can only act as corrosive agents. So some examples of each. On the non-oxidizing side, we've got some of your more classic acids. Sulfuric acid, H2SO4. Hydrochloric acid, HCl. Hydrofluoric acid, HF. Phosphoric acid, H3PO4. Acetic acid. On the other side, we've got, if you have a concentrated sulfuric acid that is also hot, it can act as an oxidizing agent. Oleum can act as an oxidizing agent. Already discussed nitric, HNO3, and perchloric, HClO4, as oxidizing acids as well. So again, for the most part, most of the acids that we encounter are on that left-hand side. Nitric acid is probably the most common oxidizing acid that we use, but it does its use does kind of pale in comparison to hydrochloric, especially, and phosphoric in certain applications. Let's talk now about pH. Now, you're probably familiar already, at least in some part, with the pH scale. The pH scale is a scale from 0 to 14. With 7 in the middle. It's a numerical scale. And for those of you that are math inclined, it is a logarithmic scale. Now, if that doesn't mean anything to you, basically what you need to know is this. On a logarithmic scale, every point increase or decrease represents a tenfold, a 10x increase or decrease in hydrogen concentration. So if we know the hydrogen concentration, we can determine the pH by taking the opposite of the logarithm of that concentration. Now, in our situations, we're rarely going to actually use that particular equation. But if you want to know how we can get a pH of 2.37 for something, that's how. And similarly, if we wanted to know the hydrogen ion concentration from the pH, we would take that pH and raise it 10 to the negative pH power. Now, I mentioned these specifically because in the lab that you do about acids and bases, there are going to be some questions that are going to ask you to convert between hydrogen ion concentration and pH. Now, fortunately for us, the pH concentration, the pH and the concentration are going to be whole number values and easy fractional values. And we'll actually give you a table to help you with the conversions in the body of the lab itself. But if we look at the two sides, on this side of the ledger, we got acidic ranges. On this side, we have basic ranges of pH. And pure water here in the middle is going to be our neutral pH. Pure water is neutral. Now, I will say that with one kind of important side note, it's really, really stinking hard to get pure water. Because if I just go up to my tap and get water out of the tap, that water has dissolved solids in it. That water has dissolved gases in it. It's actually really hard to get it without that stuff in it. Distilled water comes about as close as it can, but even in the bottling process, it's probably going to dissolve some amount of carbon dioxide and lower that pH slightly into the acidic range. When we do water testing, we generally will branch that neutral range between 6 and 8, just because outside of that range, that's usually something we have to worry about. But if we're doing just kind of general testing in our laboratory, we know that the error bars are considerable, and we wouldn't want to make recommendations for any kind of manipulation to the water lines based on pH of like 6.5, when it should be 7. So pure water, if we degas it and distill it, purify it, it would read at pH 7. Real water kind of ranges. 6, 7.5. Your blood's actually 7.4. There's a little bit of variety. All right, let's look at some methods in using pH. First problem here. I've got 3 acids that have pH values: 3.28, 5.87, 9.32. Question is this: which substance is the most acidic and which one is the most basic? Yes, absolutely. Our most acidic substance is going to be substance 1. It's got the lowest pH. And pHs ranging from 0 to 7 are considered acidic. The closer they are to 0, the more acidic we would consider them. Which of these substances is the most basic? That's exactly the opposite argument. To be substance 3. In fact, substance 3 is giving us a basic pH. We would consider substance 3 to be basic. Anything above 7, we consider basic. The closer it is to 14, the more basic it is. Okay, let's look at the second question. I have acid number 1 has a pH of 3. Acid number 2 has a pH of 6. How many times stronger is acid 1 compared to acid 2? Right. How did you come up with 30? Okay. All right. You're close. You are right. It is a 10-fold increase per number. But the effect is not additive, multiplicative. So it's actually 1,000. So 10 times 10 times 10 would be 1,000 times stronger. And you think it logically, it makes sense that way. If 3 is 10 times better than 4, and 4 is 10 times better than 5, we wouldn't add those together to make the leap from 3 to 5. We'd multiply them. 3 is 100 times better than 5. 3 is 1,000 times better than 6. 3 is 10,000 times better than 7. 3 is 10 times worse than 2. The effect has to be multiplicative. Otherwise, it wouldn't make a whole lot of sense. See a tenfold increase here. Only 1/4 increase here. Again, this is the tricky part of the logarithmic scale. You have to understand that the effect is not an additive effect, it's a multiplicative effect. And so that is where we're going to stop for today. On Friday, again, I will introduce the critical thinking assignment to you. When we finish with that, we'll talk a little bit more about pH, a little bit more about acid-base properties, and then we'll get into some actual discussions of different types of acids and bases. Have a great day.